Hi there, welcome back. In this slice of physics, we're going to continue our journey learning about electric potential, and this time we'll take a look at a parallel plate capacitor. We'll first understand the relationship between electric field and potential in a capacitor. Then we will take an example problem to determine the potential difference between the plates, and we'll use that potential difference to determine the work to move a given positive charge from the negative plate to the positive plate. Let's begin by taking a look at a parallel plate capacitor and see how the electric field is related to the potential difference between the plates. So here's a capacitor. Let's say the top plate is positively charged and the bottom plate is negatively charged. We know from previous discussions that the electric field points from the positive plate to the negative plate, and it's uniform. So if I were to show these as electric field lines, they would go from the positive plate to the negative plate. The field lines themselves will all be parallel to each other and equally spaced because the field is uniform. Now, what does that do to the electric potential? So in order to take a look at that, I'm going to take a look at a positive charge that's being held over here. Now this positive charge will be repelled by all of the positive charges on the top plate and attracted by the negative charges on the bottom plate. So it'll go down and stick to the bottom plate. If it's being held here, there has to be a force that's applied on it by maybe placing your hand over here. And the hand has to apply a force on that charge that's equal in magnitude but opposite in direction to the force that's applied by the charges on the plates. Well, what is that force? We know the electric field, and let me just notate the electric field here as E. We know that the electric field everywhere between the plates is the same value E. So where this charge is being held, the electric field is E. And if this charge itself has a value of Q, the electric force that's applied on that charge from the field would be Q times E, as we have seen before. And because the charge is positive, the direction of the force will be the same as the direction of the electric field, so down in this case. In order to counter that, the force my hand would have to apply on the charge would be equal in magnitude and opposite in direction. So the force of the hand would also have to be Q times E, but in the upward direction. So now let's pretend that I want to move this charge through a distance closer to the positive plate. So I want to move it over here, and the distance I want to move it by is distance x. How much work would I have to do to move that charge through that distance? Well, we know that work is given by the force times the displacement times the cosine of the angle between them. And in this case, since the force points up and the displacement is also up, they are aligned. The angle is 0. Cosine of 0 is simply 1. So in this case, the work is going to be a positive work since they are both aligned, and it'll simply be force times the distance. And in this case, the distance is x. And we know that the force is Q times E, so the work would simply be Q times E times x. Now, what does this work do? Similar to lifting something near the Earth, where the Earth is trying to pull it down, but we want to lift it up, we give it gravitational potential energy. In this case, we're giving this charge electric potential energy to move it from the initial point at the bottom here to the final point at the top. So this work simply goes into the change in potential energy. So delta U would be Q E X to make that movement. Now we're interested in knowing the potential difference between these 2 points. And we remember that potential energy was simply Q times the potential, which translated, as we discussed before, to delta U equals Q times delta V. So by plugging in this value for delta U, I would get Q times E times X equals Q times delta V. If I divide both sides by Q, the Q's will cancel. And so this will give me an equation that says delta V equals E times X. This is an important relationship for a parallel plate capacitor. This tells me that the potential difference between any 2 points is simply equal to the electric field times the distance between those 2 points measured along the electric field. As long as the electric field is uniform. This will not work for point charges. So let me make a note here. Only if E is uniform. And in a parallel plate capacitor, we have a situation where the electric field is uniform, so this relationship works. Moreover, you remember that the potential is positive and higher near a positive charge and negative or lower near a negative charge. So the potential will increase from the negative plate to the positive plate. And so if we want to look at the potential difference between the plates of the capacitor, and let's take the extreme. So here it was between these two arbitrary points somewhere in between, separated by a distance x. But if we want the potential difference between the negative plate and the positive plate, let's call that delta V subscript C. And let's say the distance between the plates of the parallel plate capacitor is D. This will give us a relationship for a parallel plate capacitor that says delta Vc, the potential difference between the plates of the capacitor, is nothing but the electric field between the plates times the distance between the plates. And we can also note that the positive plate is at a higher potential than the negative plate. Moreover, given the linear relationship of the potential difference to distance x or distance d, that'll make the equipotential lines look something like this. They will all be parallel to the plates because the potential at all of these points at the same distance from the positive plate or negative plate will be the same. And they are equally spaced to indicate that the potential is dropping from the positive plate to the negative plate in a uniform manner. So if we look at this as a graph, in contrast to a positive charge that was sitting at the top of a hill that got shallower as we got farther away from the charge, in the case of a parallel plate capacitor, we would have the potential drop from the positive plate to the negative plate in a uniform manner. So it'll be like a ramp or a hill with a uniform slope. So with all that in mind, let's tackle a quick example. So here we are given a parallel plate capacitor whose plates are separated by 4 millimeters. The left plate is positively charged and the right plate is negatively charged. So let me start drawing that over here. I'm given the distance between these as 4 millimeters. And it says the magnitude of the electric field midway between the plates is 1.2 times 10 to the 5 Newton per Coulomb. So over here, the electric field is given to me. And then I've been given 3 questions. What is the electric field just to the right of the positive plate? If the potential at the negative plate is given as 0 volts, what's the potential at the positive plate? And how much work is required to move a plus 1 nanocoulomb charge from the negative plate to the positive plate? Okay, let's tackle these one at a time. The first one is easy. It's asking for the electric field over here. All we got to do is remember that the electric field between the plates of a parallel plate capacitor is uniform, so it's the same everywhere. So if it was given to us at the midpoint, the electric field here is also 1.2 times 10 to the 5 Newton per Coulomb. So we're done with that. The second one asked for the potential at the positive plate once the potential at the negative plate is given. And we just derived an equation for the case of parallel plate capacitor and other situations where the electric field is uniform. We have this equation that the potential difference between any 2 points is given by the electric field times the distance between those 2 points measured along the direction of the electric field. So in the case of the parallel plate capacitor, this would simply be the electric field of 1.2 times 10 to the 5 Newton per Coulomb times the distance between the plates, which is 4 millimeters, 4.0 times 10 to the negative 3 meters. Now, electric field has 2 units that are both SI units. Newton per Coulomb is exactly the same as volt per meter. We can write this as volt per meter, and that allows me to cancel the unit of meter and get an answer for the potential difference in volts. And when you do this multiplication, you would get 4.8 times 10 to the 2 volts, which is simply 480 volts. So the potential difference between the plates is 480 volts. And so if the potential at the negative plate was 0, the positive plate is at a higher potential by that amount. So the positive plate will simply be at 480 volts. And by the way, if the question asked for the electric potential midway between the plates along this equipotential line, the answer would be just 1/2 of this because of the linear relationship between potential difference and distance. So it would be half of 480, 240 volts. The last part was asking for the work that I would require to move a plus 1 nanocoulomb charge from the negative plate all the way to the positive plate. So to do this, I just have to remind myself that the only thing that's changing as I make that movement is the potential energy. So the work would simply be equal to the potential energy gained by that positive charge, which simply is Q times delta V. I've been given Q is 1.0 times 10 to the negative 9 coulomb. I've been given potential difference as 480 volts. So when I multiply those two, I will get 4.8 times 10 to the negative 7 joules. Coulombs times volts is joules, and that's the amount of work that I will need. So this turns out to be 0.48 microjoules if you want to write it in that unit. So that's it. We solved all the three questions that we were asked. So let's recap the key points that we learned in this video. We looked at the electric potential in a parallel plate capacitor situation. First, we reminded ourselves that the electric field is uniform between the plates and used that to derive this equation for potential difference between the plates, which simply equals the electric field times the distance between the plates. And then we saw that the potential drops from the positive plate to the negative plate in a uniform manner, so it's a hill that's got a constant slope, or you can call it a ramp. And then we saw that the electric field lines are parallel to each other and equally spaced, pointing from the positive to the negative plate. So they're perpendicular to the plates but parallel to each other. Whereas the equipotential lines are parallel to the plates and also equally spaced, which makes them perpendicular to the electric field lines. Then we took a numerical example to work through some of these concepts. Thanks. See you later.